Can you start?
So, thank you and very good morning, my dear friends. Day before yesterday, I spoke about the entire lunar program of India, Chandrayaan 1, Chandrayaan 2, Chandrayaan 3. And I have spoken about the scientific rationale about studying the moon. And there I have made a mention that you have to study the moon in order to know the origin and evolution of the solar system. You have to know the moon for exploring the possibilities of doing science from the moon. So there are a lot of scientific and technological implications to study the moon. And in this discussion, I also made a mention that the basic scientific questions that drive the lunar exploration, these scientific questions necessitate the study of a few specific domains. And the domains were the domains of mineralogy, elemental composition, then the domains of exosphere, so on and so forth. And that's how I mentioned that Chandrayaan 1 mission was configured. And yesterday there was a lecture by Dr. Dania where she spoke about the major scientific results from Chandrayaan 1. And she has given a perspective of how the Chandrayaan 1 mission has transformed our idea of the idea about the moon. So while she spoke, she also made a mention that that particular mission, Chandrayaan 1, has opened up lots of surprises about the moon. Mysteries about the moon were unveiled, and they also raised a set of questions. So it happens with any mission. You hope to answer a few questions, configure a mission, and you send the mission. Some of your questions get answered, but at the same time, you get something different which you have not expected. And that's how a new set of questions emerge. And this happened in Chandrayaan 1 mission also. And that's how when we defined Chandrayaan 2 mission, configured the mission, we understood that whatever we have learned from Chandrayaan 1 in terms of the science of the moon, in terms of the capabilities of the instrument, observations, limitations of the observations, limitations of the observation strategies, those can be circumvented by different kind of configuration of the mission, and hence Chandrayaan 2 came. Chandrayaan 2 was lifted off in 2019, 22nd of July, from the Satish Dhawan Space Center, Sriharikota. And this slide, a part of this slide I have shown you in my previous lecture. But here I am going to tell you something different, what I have not told in the previous lecture. In the previous lecture, I have told you how the Chandrayaan 2 instruments were envisaged as extensions or improvements over Chandrayaan 1 instruments or payloads. I presented this table in the previous lecture also. There I have mentioned how we have grouped these instruments thematically, like hyperspectral imager, SAR, M-Cube thematically, and how in Chandrayaan 2 the IIRS instrument is doing the job of those instruments, or how the synthetic aperture radar mini-SAR, which was flown in Chandrayaan 1, how it was improved to the dual frequency synthetic aperture radar for what kind of scientific uh, results, enhanced scientific results. These things we have discussed in the previous lecture. But here you have to also understand one more aspect. Not only the improvements in the instruments capabilities were brought into Chandrayaan 2, also the observation strategy was important here. Now, here I would like to draw your attention to the left-hand side of this slide, wherein I have drawn a picture of the Earth and the orbit of the moon and the sun. So this is a picture which you see if you imagine the Earth in the middle, and with respect to the Earth, you are noting down the different locations of the moon and the sun. So you can think of different geometries. Okay, so the different geometries of the orbit give rise to certain seasons. Like the way we have seasons on the Earth, depending on the orbit of the Earth around the sun. Similarly, you imagine that you are sitting on the Earth, and the moon is revolving around the Earth. Around the moon, the Chandrayaan 2 is there, which is revolving around the moon, and there is a relative motion of the sun also. Depending on the frame of reference, your perspective changes, and that is what is given in this picture. And here, the two distinct seasons were defined, which one is dawn-dusk season. The angle between the sun and the orbital plane is more than 30 degrees. So what is this? Let us try to understand this. One is angle between the sun and the orbital plane. So if you have a vector, say with reference to the moon, one is going to the sun, that vector, and the orbital plane means the orbit of Chandrayaan 2 around the moon. That orbits plane, there may be an angle. So that angle I am referring to here. That angle, if it is more than 30 degrees, we call it a dawn-dusk season. And if this angle is less than 30 degrees, we call it a noon-midnight season. So I think this nomenclature is very much clear, because this is very important to understand which instrument is to be operated when. There are some instruments which have to be operated in the dawn-dusk season. There are some instruments which have to be operated in the noon-midnight season. Depending on the, there are some instruments which can be operated irrespective of this. Continuously, this can be operated. So it depends on the observation you wish to make, and whether sun has got any role to play in the observation. All these things play important role. As for example, if you notice this color code at the bottom of this slide, see some of the instruments along the Chandrayaan 2 column I have written in blue color. All season operation, irrespective of dawn, dusk, or noon, midnight operation. The one which is pitch color, constraint based, this is a very complicated thing. These kinds of instruments, only one instrument is there corresponding to this, the DFRS instrument, and orbital high resolution camera also falls into this. Constraint based means illumination condition or a specific orbit is needed for this kind of observation. These are all constraint based. You cannot say that this is noon midnight session or the dawn dusk session. When the opportunity comes, opportunity may happen in terms of proper illumination of the surface. Okay, that is typical of imaging instruments like OHRC, or special conditions may come when you are looking for a special geometry of electromagnetic waves passing from Chandrayaan to your ground station. You want to have an occultation, radio occultation, that also needs a specific geometry. So these are special constraint-based operations. And then there are some instruments which are ought to be operated for the dawn-dusk season, like DFSAR, or there are some instruments which are for the noon-midnight season, IIRS and TMC2. So like this, there are different instruments which are to be operated at different seasons, or when the opportunity comes for this particular observation which you wish to do. This you have to understand, because I'm spending a lot of time on this slide, because see, in this 1 hour lecture, the objective is not to tell about the great depth of science of each and every payload. We don't have time for that. But what we should do is to appreciate, when you define a space mission, what all the things get into it. Not only the instruments, you also have to know the observation geometry, the opportune moments of observation, plan your observation in accordance with the different astronomical bodies, and then only you will be able to utilize your mission properly. So this is the whole picture of Chandrayaan 1 to Chandrayaan 2. How did we have the transformation? Now, having said this, let me tell you about a few scientific results from Chandrayaan 2. So you remember that Dania spoke about the Chase-1 instrument which flew in the Moon Impact Probe. And I also remember I spoke about the Moon Impact Probe and Chase when I spoke day before yesterday about the Moon Impact Probe mission. So this instrument is basically a mass spectrometer. A mass spectrometer who you are listening for the first time, it is like an electronic nose. So there are some people who can smell a food and predict what are the ingredients that have gone into making of the food. So electronic nose is something like this. It can sniff and it can tell what are the composition in a mixture of different gases. A mass spectrometer is a similar instrument wherein it can analyze the relative abundance of different gas atoms and molecules in a mixture. And this kinds of instrument was sent to moon in the Chandrayaan-1 mission, because the composition of the moon exosphere is very important, because it carries a lot of information about the evolution of the atmosphere. Not only evolution of the atmosphere, also it speaks about, to a certain extent, what is happening in the internal part of the moon. So you might think, what is the connection between what is happening in the internal part of the moon and what you see in the atmosphere? Very valid question. The answer is, see, here this graph, this result what you are going to see, it is about a gas called argon 40. Okay, so argon 40 gas is a result of the radioactive transformation of potassium 40. So potassium 40 is a radiogenic nuclide, so which transforms to argon 40. Now, what happens if you dig the moon surface to up to tens of kilometers, 10 kilometer, 20 kilometer, 30 kilometer around? In that region, there is a good reservoir of, in many places, potassium 40. And if there is an orifice or fissure in the moon's interior through which some gas might come out, can find passage to come out, and those gases can become a part of the exosphere. So then whatever gases are there in the internal part of the moon, they can sneak out in the atmosphere. So if you have a mass spectrometer in the atmosphere of the moon, and if you find some signature of some gas which is supposed to be inside, you can also infer about what is happening in the interior. So as for example, if you want to know argon 40 in the moon's atmosphere or exosphere, you will be in a position to understand the radiogenic activities which are happening in the moon's interiors. So that is the importance of this. And here I would like to tell you, there have been low latitude observations of the moon, argon, from the Apollo 17. See, this is such a topic. This is not the one which we are attacking for the first time. Moon's exosphere, composition, argon, these are all decades old problem. And as early as Apollo 17, they started in situ observation on this. And however, their observations were not successful during the daytime, because the dynamic range of the instrument was not sufficient. Instrument basically was getting saturated in the daytime. And what is to happen? There was a gap in the understanding. Then the neutral mass spectrometer was flown in the LADEE orbiter. LADEE is a mission from NASA. So they flew on the neutral mass spectrometer. They also studied, but LADEE's observations were limited to the lower latitudes, because it was a near equatorial orbit mission, and its observations were limited to plus minus 30 degrees. But there was no understanding about what is happening in the global scale. In order to have something in the global scale, you need to have an orbiter which is a polar orbiter, right? So if you have a polar orbiter, you can make use of the rotation of the orbiter and the rotation of the moon in order to cover the entire moon. So, and Chandrayaan-2 did the same thing. There was a mass spectrometer called CHASE-2, and it was having opportunity to see the entire globe of the moon. And that's how the argon 40's entire mapping was done. The variation of the argon 40 gas at different parts of the day was studied. And argon 40 gas is a condensable gas. Those who remember your chemistry lessons, you would remember there are certain gases who, condense at a temperature, at a very, very low temperature. So argon 40 has a tendency for this. And then the temperature increases when sun rises. then it comes out of the condensed state and becomes a gas again. So this kind of signature, this kind of temperature variations, how you can see the temperature variations when you have a transition from night to day. So this is called a diurnal variation. Okay, the night side argon should condense, day side argon should come out. And temperature variations also you can see when you go to the equator to the poles. And also you can see the variations where you have patches of enhancements of say potassium, which can give rise to argon. So what I want to say that there are a lot of reasons for the variabilities, even for argon when you study. And these variabilities make the thing different. Had everything been uniform, you wouldn't have found the motivation to study this. So there are variability in terms of spatial features. There are variabilities in terms of diurnal variation. And there is a lot of process which are happening in terms of the dynamics of this atoms of argon-40 with the moon surface. So in a nutshell, I would like to tell you here that these observations of argon, these are all indicative of unknown or additional loss processes or moonquakes. If moonquake happens, what will happen if something is trapped inside? Those were not coming out otherwise, they will find some way to come out and become a part of the exosphere. So moonquakes and regions with lower activation energies, which need further investigation and call for better understanding. See here, the indication which is given from this slide is, it has been a giant leap from the understanding from the previous missions, no doubt about that. Yet the observations prompted some more investigations on this particular topic. So the next missions, not necessarily be from India alone, any other country might think of designing a similar instrument, maybe with a different kinds of geometry of the orbit or different kinds of strategy altogether can be adopted to understand this problem better. So now there have been another observation on the electron density with dual frequency radio science instrument. And as I was explaining on the previous day, there is a technique called radio occultation. So somebody asked me that if you have to study plasma in any planetary body, what are the techniques? So while answering, I made a mention that radio occultation is a technique. And radio occultation is a technique which is used to probe the atmosphere or ionosphere of any celestial body. It could be a planet, it could be a natural satellite. By measuring, so what do you measure in this experiment? The changes in the radio signal. To be more precise, the phase changes in the radio signal as it passes through the body's atmosphere or the ionosphere. Now, this Chandrayaan-2 dual frequency radio science experiment, it uses dual frequency. One is in S band, the other is in the X band. S band, this is 2 to 4 gigahertz. The X band is defined as 8 to 12 gigahertz. So the use of two frequencies in this technique can improve the quality and accuracy of the data obtained, and during the differential change in the properties of the two waves, like when the S band wave is passing and the X band wave is passing, S band frequency wave is having lower frequency compared to X band. So when two different kinds of electromagnetic wave pass through a given region and the medium introduces some change in the two waves, the two waves are affected in two different ways. Now, if you have a single wave, you will not be able to compare with any other wave. So having two waves, two frequencies, make the measurement more accurate because you are capable of understanding the difference in the changes in these two waves when both of the waves propagate through the medium. And this is what has been done in the DFRS experiment. If we remember, Chandrayaan-1 also had a similar experiment wherein it was a single frequency. So this is definitely an improvement. So here in this slide, in the top left panel, if you see, this is the geometry, which is called the ray tracing geometry of the radio signals in the lunar atmosphere. This is the moon. And so what is happening here, I am trying to show when the radio frequency wave passes, So what are the regions of the exosphere and the ionosphere which properties of the electromagnetic radiation? And this is basically the technique of the radio occultation. Then in the top right here, I think you're able to see my cursor. The comparison of the observed and simulated ray path, integrated electron density for the Chandrayaan-2 orbit, a particular orbit. So what is happening, our colleagues in the Space Physics Lab, Vikram Sarabhai Space Center, they have done some theoretical modeling. They have assumed that if these kinds of neutral atoms and molecules are there, if those neutral atoms and molecules are getting ionized, what should be their density and what should be their composition at different heights of the moon. And if you have an electromagnetic wave which passes through that region, what are the kinds of changes the electromagnetic radiation should see, and from the changes, how can you convert the changes to the inference about electron density in those regions of ionosphere. So this is the process of modeling. Now, what happened? I was making a mention about a model which was prepared by our colleagues at Space Physics Lab. The model is called 3D LIM. 3D means you understand the 3 dimension. A lunar ionosphere model, LIM, for 3 different conditions: lunar wake. Lunar wake I have explained on the previous day. Solar terminated and local moon. For these 3 conditions, they have simulated the condition. And electron density is of an order of magnitude higher inside the lunar wake region. And the bottom right panel shows the altitude, latitude, and longitude variations of the electron density along the path as simulated by 3D LIM. You don't have to be carried away by a lot of things which I'm telling on this slide. You can forget and you think like this. You think a very simple manner. Moon is having a very tenuous atmosphere, very less atmosphere, but it is not zero. It is called an exosphere, but it cannot be a zero number density. So if you have some finite number of atoms and molecules, some of them will be ionized because of the solar radiation. And some of them are ionized, means there is a very thin ionosphere around the moon. And when you have a thin ionosphere around the moon, if any radio wave passes through it, there will be some effect on those propagation properties of the waves. So this slide tells about the observations which have come out from Chandrayaan-2 and also the kinds of simulation our colleagues have done. So the message here is, if any one of you are interested to know more about this or to be a part of this project, want to use the 3D LIM model, you can contact the Space Physics Lab Vikram Sarabhai Space Center, who is the custodian of this 3D LIM model. The data of the occultation, anyway, you can always get from the Indian Space Science Data Center, which I spoke about day before yesterday, and there will be a lecture also. So coming to another domain, so whatever I have told so far, previous result and the one previous to previous one, all this were about what is happening on the exosphere and the ionosphere. I started from argon, and then I started speaking about the radio occultation technique, about we spoke about the electron density and plasma properties at different heights. Here, I made a mention on the previous day. I would like to repeat it. Radio occultation has some limitations. One limitation is it cannot go very close to the surface because of the design of the experiment. And also, when it measures in an integrated density, integrated view along the path of propagation. So that's why it has a difference between in situ measurement and radio occultation measurement. But in situ measurement is not possible at different heights, right? But radio occultation is very good experiment if you want to study what is happening at different heights globally. So every method has got its own USP, in situ and the auto technique. Anyways, let's come back to surface. So as I was mentioning, Chandrayaan-2 was having instruments which could measure the surface elemental composition of the moon, which is very much important from the point of view if you want to know the basic building blocks of the solar system when it got started, And when it all started, everything was molten. It was temperature was so hot, it was everything was molten, and there was a tension between gravitation and surface tension of those molten bodies, and uh, any body assumes a shape of a sphere as a common tendency because the surface area becomes minimized. So when in this process, there was a process called planetary differentiation. The planetary differentiation means um, there were heavier materials, there were lighter materials. The heavier materials had a tendency to sink. Sink means to go near to the core or interior of the bulk. On the contrary, the lighter ones, because of their buoyancy, they started floating. So they constituted the upper mantle and the crust. So this is a process of planetary differentiation, which has happened with the many rocky bodies in the solar system. And if you have to understand what are there on the upper part, upper crust of the moon or any other celestial body, one technique is the XRF technique. XRF technique is X-ray fluorescence technique. What happens in XRF? See, XRF technique is not specifically for space applications. XRF technique people use in ground also. As for example, if you want to do a non-destructive testing of any material, you want to know its composition, surface composition. In forensics also, you can use. So what happens, you impinge the surface with some X-ray. And when you impinge some X-ray on the surface, some of the atoms get excited because of this incidence of the X-rays. And upon excitement, when they undergo a process of relaxation, they emit some photons. Those atoms on the surface emit some photons. Those photons are also in the X-ray regime. That is a separate story. But what is important is the energy which comes out because of the process of relaxation of the atoms. They carry the signature of the energy levels of the atoms. So as you're aware from your basic physics, that every atom has got its own atomic levels, right? And these transitions of different from one level to the other in any given atom is a fingerprint signature. Just like we have fingerprints, so my fingerprint will not match with any other person's fingerprint. Similarly, the transitions of from one energy to the other, atomic transitions of a given atom, its signature is unique signature, which can be captured if you shine the surface with an X-ray. So that is what happens on the ground. What will happen in space? In space, you need not carry an X-ray because sun is there. And sun is a broadband source of electromagnetic radiation. And sun also has a component of X-ray in it. So X-ray come and hit the moon surface. And what happens? Same thing happens. The atoms on the moon surface get excited, and then they undergo a process of relaxation, and during the process of relaxation they emit photons. And this instrument which I am mentioning about here, class instrument, this instrument captures the signature of the X-rays which are coming from the surface of the moon, and it captures the different signatures of different elements. So this is how this thing works. Here I would also like to mention that this kind of instrument we have flown in the Chandrayaan-1 also. If you remember, one instrument was named as KICS. The way in which we used to write KICS is very, very peculiar. If you don't know, if you don't have a background, you will pronounce it as C1XX. So it is not C1XS. It is called KICS with this peak. So KICS detected sodium from the characteristic line in the X-rays, and it opened up the possibility of measurement of more sodium, because you have to remember one thing. When we have sent Chandrayaan-1 lasted only for 10 months or 1 year. Okay, and 2008 the year was. You remember 2008 was a period of less solar activity, low solar activity. And when was the period of low solar activity? The emissions in the X-ray region of the sun, or UV or X-ray region of the sun, they are not adequate. For a class kind of instrument, when you are counting on sun, the sun will give X-rays, emit X-rays, and in that X-ray shine of the sun, I will see what is coming out as X-rays from the moon. So you're assuming basically that sun is emitting a good amount of X-ray. But this condition was not satisfied in 2008 because of the solar activity was less. And many of you are aware that sun has got an 11-year cycle. So 11-year cycle was there after 2008. If you add 11, it is 2019. Chandrayaan 2 also flew in 2019. Yeah, 2019 also solar activity was less. But Chandrayaan 2, you have to remember, it is still working. And Chandrayaan 2 is very lucky because it has seen the rising phase of the solar activity. 2019, 20, 21, 22, 23. Now it is solar maximum is coming, right? So it has seen this transformation of the solar activity. And there have been many occasions of solar flare. So I will speak a bit later when I speak about one more instrument about the solar flares. So class could see more sodium, or it was in a position to do a global mapping of the sodium for the first time. So what was found in the study? It was found that a part of the signal which was coming, which told that it is sodium, it could be arising from a thin layer of sodium atoms which was weakly bound to the lunar grains. Okay, and those sodium atoms can be released from the surface by the solar wind or the ultraviolet radiation more easily than if they're part of any lunar minerals. So, there have been many observations from the ground observatories where people have telescopes, and from the telescopes they look at the moon, and what do they look? Their telescopes might have some filters which are tuned to what? The emissions of the sodium lines. So many of you are aware of the sodium D1 and D2 lines. So sodium lines are the ones which can be filtered to be seen from the ground telescopes. And people have seen the sodium which are coming out of the moon's surface as a, what should I say? I should say a sodium corona, like solar corona. And this term is not wrong. People use these kinds of terms: hydrogen corona, helium corona, so a kind of sodium corona. Okay, and this is possible because the sodium are loosely bound, and if you have a good amount of deposition of energy, either in terms of solar wind depositing some energy or UV radiation depositing some energy, there could be a process of sputtering. On the previous day, Dania spoke about sputtering, right? So this sputtering is a process by which you can use some external energy to liberate some of the atoms out of it. So had this sodium been a strongly bound sodium, a part of mineral, you would not have found them from the ground observations like the VOC. They must be from the loosely bound, not a part of a mineral, and they are also amenable to the XRF technique, so that you can see what is happening in the global scale. And also shown is a diurnal variation of the sodium, and that would explain the continuous supply of atoms in the exosphere sustaining it. Now here you might ask a very logical question, that is, if sodium is available and it is not very tightly bound, loosely bound, it should be a part of the exosphere also, right? They're getting sputtered, so they should be a part of exosphere. The answer is yes. So your next question would be whether the CHASE-2 instrument has said it. Then the answer will be no, as far as my knowledge goes at present. The reason could be at 100 kilometer, wherever CHASE-2 is making measurements. You have to remember CHASE-2 is not doing remote sensing measurement. CHASE-2 is doing in situ measurement. That means if some of the sodium atoms are at 100 kilometer altitude, and if they are in the nose of the mass spectrometer, then only they will be measured. And given the minimum detection capability of CHASE-2 and the possibility of having that many number of sodium atoms at 100 kilometer altitude, this opportune moment didn't come. So as far as my knowledge goes, Chase 2 so far has not seen sodium in the at 100-kilometer heights. But this indeed is a very important result, I must say. So likewise, as I told about sodium, there have been detection of other elements like magnesium, aluminum, silicon I have shown here. And the bottom panel of the picture you see, this bottom panel is a glimpse of how the data look like. The data means how the process data, of course, not the raw data. So in the x-axis, I have plotted energy in kilovolt, and the y-axis, it is the strength of the signal. So strength of the signal means which signal? The X-ray which is coming from the surface of the moon. That signal strength. So this spectrum we call XRF spectrum during peak 100-second of an X 1.5 flare. So there are different terms here. You know, when we speak about solar flare, there are some flares which are very less intense. There are some flares which are of medium intensity, some flares which are really intense. So there are different classes of flares, A class, B class, so on and so forth. So I'm not going to those discussion. All that I wanted to tell, X class is kind of flare which is quite a strong intensity flare. And if you have such a strong intensity of flare, it is conducive for an XRF measurement. And such an XRF spectrum, which was obtained during an X-class flare, is plotted here, wherein you can see the signatures of different species. So when this XRF was acquired, of course, it was from a particular location of the moon, and you have to go on acquiring from different locations, and that's how you can come out with these kinds of maps, like the map I have shown in the previous slide for sodium. In this slide, I am showing for magnesium, aluminum, silicon. Okay, and also there have been some detection of minor elements like chromium, manganese. So class instrument had a spatial resolution of 12.5 kilometer. So with a 12.5 kilometer is a pretty good number, because the elemental composition, you don't expect much of a variation, much of a significant variation spatially. Large scale, yes, but 12.5 kilometer is a pretty good resolution spatial scale to understand these kinds of elemental composition. So, so for what have I spoken about? I spoke about argon. I spoke about the lunar ionosphere. I spoke about elemental composition, right? Then coming to another interesting domain, term is flying hydration. So hydration, as I mentioned in my previous lecture, hydration means something to do about hydro. Hydro means water, right? So water on moon. I also made a mention that the moon mineralogy mapper instrument was limited to the wavelength of 3 micron. Okay, and the signature which the moon mineralogy mapper obtained from the polar regions of the moon, they were the absorption dips from the hydroxyl radical, not the water. Okay, in order to capture the spectral dip, the kind of dip which you are seeing here, I hope you are able to see my cursor. These are called spectral dips. I was mentioning in my lecture. So if you have to capture that for water, your instrument should have a capability to go beyond 3 micron, because water comes somewhere here. And there are other spectral signatures also in the higher wavelength region. More than 3, beyond 3, especially 6 micron, there are features. But what I wanted to say, M-cube or moon mineralogy mapper was limited to 3 micron, and it could unambiguously see hydroxyl radical. And there was an inference that this hydroxyl could have been due to water ice. Since the wavelength range was up to 3 micron, moon mineralogy mapper could see the 1/2 of the dip. Had it been more in terms of the wavelength coverage, it would have seen the rising part also. Okay. Now, IIRS instrument had a spectral range which is 0.8 to 5.0 micrometer. and its high spatial resolution, 80 meter, and extended spectral range up to 5 micron, it made it more suitable to completely characterize the lunar hydration in the typically the region which is in the region of 2.8 to 3.5 micrometer region. You will have signatures of hydroxyl, you will have signatures of water also. Now, lunar hydration absorption at 3 micron has been observed to be present at all latitudes and surface types. Very important statement, my dear friends. All latitudes. It is not only at the poles. This water signature has been found at all latitudes and surface types with varying degree for all pixels in study area between 29 degree to 62 degree. And the spectral absorption depth also shows distinct variability associated with lunar mineralogy. Different kinds of minerals trap water in a different ways, surface temperature and latitudinal dependence. Also, you have to remember this water, especially the water which are water molecules which are not trapped, which are loosely bound, they will have a tendency either to get dissociated to OH and H, okay, because of the ultraviolet energy from the sun. And some of them will not be dissociated, some of them will be ionized and will be picked up by the solar wind. And there is an overall tendency of hopping of the water from the lower latitude towards the poles and towards the night side, because they are having a tendency to hop in the direction of the negative temperature gradient. Okay, so that is the reason why you have found a good kind of spatial variability in the hydration features of the moon. Now, from this observation, it is suggested that hydroxyl retention is more associated with space weathered mare surfaces, the mare regions of the moon, at higher temperature, which is typically more than 320 Kelvin, with coarse grained, bright, plagioclase rich, fresh surfaces are relatively H2O dominated due to solar wind implantation. Very complicated statement. If you are not an expert, very difficult for you to understand, but very easy language. I will tell you what I wanted to convey to you. See, the solar wind is having hydrogen, right? And your surface of the moon is having lots of compounds which are containing oxygen. So there is a reaction between this hydrogen and the oxygen, and that is one of the mechanisms of the formation of water on moon. The other mechanisms also. Now, this observation tells there are different kinds of variability of different kinds of minerals and types of regions on the moon, and there's a temperature dependent also. These factors will depend how efficient will be the process of generating OH and eventually H2O by this process of using the solar wind and the local hydrogen on the moon surface. A lot of variability was that only this instrument brought out. Then there was also another result for proposed mission between ISRO and the Japanese Space Agency JAXA. This is not a mission which is approved yet. The mission is planning to go to the polar regions of the moon, polar region of the moon, southern polar region of the moon, near a permanently shadowed region in search for lunar water and volatiles. So this IIRS instrument has done lot of analysis near the possible landing site at the Shackleton crater. So these IIRS data have successfully captured the presence of hydration at the lunar south pole of the proposed LUPEX landing site. And what has happened was there was a detailed spectral analysis from this IIRS instrument, and there was a difference between the previous observation. While the moon mineralogy mapper proposed that the water amount could be 1,000 parts per million, this IIRS told that there will be a diurnal variation also, and the variation could be anything between 700 ppm to 1400 ppm. And the future landed rover missions for the lunar polar exploration would require definitely high resolution infrared spectrometers with an active illumination source for the permanently shadowed regions for complete understanding of the lunar hydration features, and also to infer the nature and the quantity of the hydration species. And these measurements, which are done by IIRS, will definitely act as a ground truth. And what is meant by the ground truth? Because if you have these kinds of numbers, anything between 700 to 1400 ppm, and then when somebody wants to send a rover there and have in situ observations, their instruments detection limit should be designed in accordance with whatever number these kinds of missions like Chandrayaan 2 or Chandrayaan 1 they are proposing from time to time. So according to the instruments sensitivity, instruments different parameters of operation like integration time, etc., those will be configured to cater these kinds of needs. And that is why I mentioned in my previous lecture, one mission stands on the shoulder of the other. And there have been another set of results like detection, characterization, and quantification of hydration features at other craters like aristocrats, and utilizing appropriate thermal correction approaches, different volcanic regions which were studied during MC observations also have been studied, and the hydration features also were studied because of the volcanism. And this is very important, my friend, because water on moon have got different sources. One I already mentioned. The thing which I mentioned about is what solar wind is coming, and you're having chemical reaction between that hydrogen which is coming from sun and molecules of atoms of oxygen which are on the minerals of the moon. They are reacting. That is one of the mechanisms. Another mechanism is the intrinsic water or endogenic water of the moon, which was shared between what? When the moon was formed by the great impact uh, between a Mars-sized object Theia and the Earth, proto-Earth. They impacted, and there was a lot of ejecta which came out, and they had a process of uh, coalition of the fragments, and then a part of the fragmented Earth and the part of this Theia, the impactor, they combined to form the moon. In this process, the volatiles which were there, they got shared, and some of the volatiles they got captured. The majority got captured by the Earth. Some of the volatiles, including water, got captured by the moon. And whatever water trapped signature you're getting, which is coming from interior, either it is coming as a volcanic activity, but is coming, whatever is inside it coming out, or because of a sample return mission, you are having access, you're bringing out something, and then you are trying to infer. Those measurements are representative of the endogenic water in the moon. Also, there is another process wherein the cometary gardening happens. Cometary gardening means comets are having good repository of water. They come and get bombarded on the moon surface, and that is another kinds of mechanism how water is coming, and same way water has come on the Earth also. So this result I will not dwell much. I have made a mention, not only mention, I remember I have discussed also about the orbital high resolution camera, and also I told about its scientific importance and its technological importance as well. So this has a resolution of around 25 centimeter when you see from the directly from the upward distance, which is called the Nadir direction in technical terms. So in Nadir direction, the spatial resolution is about 25 centimeter, and you can see the pictures of Menzies and Sympelius craters with a very good, and I should say unprecedented spatial resolution. And I also mentioned what is the importance of being able to detect the smaller structures, small boulders or small craters in terms of planning of this future missions, also in terms of understanding the impact processes and what kind of repercussions that happen after an impact on a surface. And also the geochronological applications wherein you try to correlate between the isotope chronology and the crater size distribution of a given region. These kinds of techniques work. So analysis of boulder regions also has been done. So these results I didn't show you in the previous lecture. So lunar lander and the rover explorations bothered about the small boulders, and OHRC has identified and mapped a total of around more than, I should say, 2,000 boulders having diameters which are ranging from a bit more than 1 meter to more than 6 meter, and they calculated the heights also in the range of say, 0.2 meter to more than 4 meter. So pretty good structures, and these kinds of boulders you can see if you travel in the city of Hampi in Karnataka, you will be able to see lots of boulders of those sizes, and they're quite important. Just imagine if you have those kinds of boulders, you're traveling to Hampi, and some kind of boulders have been on the road, and you're traveling with a car, what will happen? Same thing you can imagine if you have a rover or a lander and this size of the boulders are present, what is going to happen? Okay, so this analysis indicate the different kinds of processes which have happened in kinds of this fragmentation. I'm not going to those details because I have to take a lot of geological terms on this. I don't want to go too deep into the technicalities. Now, this boulder distribution, I must tell you, the distribution with the size distribution is taken as a proxy to the age of the crater, and the crater age is estimated around 50 to 90 million and 50 to 90 million years. So the size distribution of the boulders is not limited to hazard detection or hazard quantification, but also tells you indirectly about the estimated size, estimated age of the crater. So in geology, these terms are very much common. You often mix the science of finding something's age, which we call chronology, with the features, with different techniques. Then identification of potential domes from the OHRC image. A group of potential domes also were identified from the OHRC image, and craters were mapped over the domes, and the cumulative size frequency distribution, which is a very important technique in geology. This was analyzed, and there's a technique wherein from this variation of the cumulative crater frequency distribution curve, you can estimate the possible age of that region of interest, and the age was estimated as in the order of 64 million years. And the young age, 64 million years, it is a young age, I should say, because geologically we speak of millions of years, billions of years. So 64 billion years is comparatively young in the geological scale. They indicate recent lunar volcanism. And it is like a detective story altogether. See, to what extent we have gone. We started by telling we have a high resolution camera called OHRC. We are capable of seeing the small structures. Then we told that what do we get? What important thing we get if we see some small structure? Then I told about hazards, and then I told about estimating the age. Now I'm telling from this estimation of the age and the basic fact that you are seeing something in the volcanic signature region, which tells about the recent lunar volcanism. So one inference from the other in steps you are doing. So what is the importance of this statement? The importance of this statement is in the recent geological years, if you have a signature of volcanism, it means moon has not yet depleted or finished its internal energy. There are instances when volcanism happens on moon, may not be very regular as some of the members of the solar system, but it has not become zero. It has not become completely dead geologically. Now, this also is a very big question, how moon being a smaller body compared to many other bodies in the solar system could retain its internal energy. What is the mechanism? How did the heat get retained? Because from the basic physics, we know if a body is bigger, more massive, its heat capacity is also big. But how is it so happen? How is it retained? Whether the kinds of thermal conductivity of the regolith or thermal conductivity of the mantle or the entirety which comes between the core and the surface play a significant role? So that is an open question. Then TMC2 terrain mapping camera, this quantified different processes of the geological structures like lunar crustal shortening, which is a process on the moon where the crust, lunar crust undergoes compression or gets squeezed horizontally. Here, this cartoon tries to explain. And what happens? It leads to the reduction of its overall size to the lateral extent. And this phenomenon is similar to the tectonic compression, which happens on the Earth, where the tectonic plates can collide, and which can lead to the crustal shortening and the formation of different mountain ranges. If you're remembering the geography lessons, you are definitely able to appreciate these kinds of things. And also, if you if you're a good chef, if you have made cakes, and you must have noticed what happens when you are done with the batter and you have kept the batter in a pot in the microwave oven, done the process, and you have left it for cooling, what kind of deformations have happened on the upper part of the cake? So try making a cake and you will have a feeling of these geological processes. And TMC2 with its images could also quantify this process of crustal shortening. So time is limited. I will not go. I am tempted to tell more, but many things to tell. Lunar neotectonism from the TMC2. Neotectonism means recent or very recent, relatively recent lunar geological activity or tectonic processes, which also indicates that a lot of manifestation is happening of the internal energy of the moon. Okay, so let us not go to those details of the process. And age estimation also has happened, say 1.9 million years, a very recent age, extensional structural feature, and probably not related to the older Mari volcanism. Friends, 1.9 million years is very young geologically. Those who have studied geology will appreciate something is happening. Moon always. So let us go very fast now. This picture shows some images from the Chandrayaan-2 L-band synthetic aperture radar, which reveals some structures which you are not able to see otherwise, some craters which are hidden below the surface. Okay, because sometimes the process of resurfacing happens. There is a crater, and due to some reason, some fragmentation or some impact process nearby, things get deposited over a crater, and you cannot see if you are seeing with a visible imaging system. So these kinds of RF signals, RF waves are able to give you access to the view of the structures which are below the surface. So this is one of the pictures. The right-hand side shows the optical images from the Lunar Reconnaissance Orbiter, and the left-hand side shows the radar image from Chandrayaan-2. So there have been other results also, and the dual frequency synthetic aperture radar has studied the ejecta of different kinds of young and fresh craters, along with the interiors of some of the permanently shadowed regions, which is shown here. And one ambiguity with respect to dual frequency synthetic aperture radar is it can provide some signature which you can interpret the presence of as a presence of water, or also you can interpret as the roughness of the surface, scattering properties of the surface. So it is very tricky to understand the kinds of hydration and the kind of scattering property unambiguously. And there is a lot of open activities which are there. And those of you who are interested to pursue research in this area, you are most welcome to contact the principal investigators. And the data are all open in the public domain. So this gives again a list of what kind of other significant results have come from DFSR, retrieval of lunar surface physical parameters, water rise at PSRs, lunar volcanism, impact melts, landing hazard detection, which is very important for the next missions, so on and so forth. But here I would also like to mention that when I was speaking about the XRF technique, we remember a few minutes back, class observations, wherein I have mentioned that sun is shining X-ray, and XRF you're seeing when you're looking at the moon. Now, if you don't know the input, sun's X-ray is the input, and the cause, the effect is the X-ray which is coming from the moon. So if you are studying only the cause, only the effect, but not the cause, your understanding is not complete. So you have to have a proper understanding of the X-ray which is coming from the sun, and also the X-ray which is coming out of the moon, so that you can have a good way of comparing them and lead to the quantification of different elements. So this instrument which was studying the X-ray from the sun was XSM, X-ray solar monitor. It has characterized the solar energy distribution from the range of 1 to 15 kilo electron volt at different conditions of solar flare intensities. So remember, I was telling, starting from 2019 till date, Chandrayaan 2 mission could see the different, conditions of activity of the sun. It was going from solar minimum to solar maximum. And long-term XSM light curve you are seeing here for the solar cycle 25, we are undergoing the solar cycle 25 now, where the 1.8 angstrom flux is plotted as the proxy with time. And there are short period oscillations also seen. They're all short-term signatures. Now, the solar X-ray light curve obtained from XSM during the first two seasons, they are all plotted here. And the blue shaded regions, which are shown here, I hope you are able to see my cursor. These regions correspond to the regions of the quiet sun, where no active regions, and the red bars which are shown here, small red bars you are showing here, they're very less in number. These regions indicates the microflares observed during those periods. So this blue region are the times when sun is not that active, and the red regions are the one where you are seeing some microflares. Means, first lesson is, even when sun is not active, it is not that flares don't happen. Easy language. Flares go on happening, although they are microflares, but they are always happening, just like a basic biological process is happening. Those who remember your lessons in biology, you will remember you have come across a term called basal metabolic rate. So the basal metabolic rate is always some processes are happening in your body. Some voluntary operations, involuntary operations, your body temperature is maintained. Always some processes are happening. And similarly, similarly things happen in sun also. In the quiet sun region period also, always something is happening because sun is dynamic, and the microflares are happening during those periods as well. And around 98 X-ray microflares in quiet sun was observed by XSM, and with few previous measurements, and they have lower temperature and emission measured compared to the active flare regions. Now, I will not go to the much of details because this observation has got a lot of things which needs discussion in much depth. I need not do this. This is not the objective of this lecture. All that I wanted to give you an impression that, number one, Chandrayaan 2 not only studied about the moon, it studied about the sun also. Number two, what it observed was, even during the quiet sun period, sun has got microflares, and that has got something to do with the answering to the coronal heating problem, wherein it is an understanding that the solar corona is a lot more hot, a few million Kelvin, wherein the characteristic temperature which we can see of the sun is indicative of a temperature in the order of 6,000 Kelvin. Okay, this is called the coronal heating problem, and the continuous process which is known as a DC process, which is happening on sun, is also having something to contribute to the process, and those are captured by the XSM. And XSM has also captured the process of flares which are happening when sun has started becoming active, and now it will capture more. Okay, I think I have told about this coronal heating and elemental abundance. elemental abundances in the X-ray. When I'm telling about elemental abundance, this is not the elemental abundance of the moon. Elemental abundance of the moon was studied by class. The X-ray signatures from the sun also carried the fingerprints of the elemental species present in the sun. So here, this experiment of XSM not only contributed to aid the class measurements, but also did independent measurements of the sun in terms of understanding to a certain extent the coronal heating problem, the elemental abundance, as well as the physics of the flares from the sun. And also, Chandrayaan 2 had occasions when it passed through the geomagnetic tail. Those who don't know what is a geomagnetic tail, for them, let me tell you, Earth has a magnetic field, and the Earth's magnetic field is not sphere. That is a different story altogether. What I wanted to tell is Earth's magnetic field, geomagnetic field, has a very big asymmetry. Asymmetry happens because of the interaction between the sun, especially the solar magnetic field and the Earth's magnetic field. There is a kind of tapering of the Earth's magnetic field in the anti-sun side. And if you visualize the orbit of Chandrayaan 2, there has been occasions when the Chandrayaan 2 was passing through this oblong part of the geomagnetic region, which is called the geomagnetic tail or geotail. So it was having a transition. So what has happened? What is so special there? So a lot of dynamics of charge particles happen because solar winds are coming and they follow the magnetic field lines. And in those regions, there is an accumulation of a lot of high energy charge particles. And this class instrument captured some of those. Captured means observed some of those. So the Earth's geomagnetic tail experiences interactions of the magnetized solar wind with the Earth's magnetosphere and leading to several plasma processes, as I have mentioned. And the class has picked up because class is not only sensitive to X-rays, it's also sensitive to energetic particles in that energy region. And class has observed. So what did class see? Enhanced particle flux during the transit through the geomagnetic tail. And this result is very important if you are planning for any human space mission, wherein human beings are supposed to pass. So this particular observation will give a lot of clue about the radiation environment, if at all any human being is supposed to pass through that region in the human lunar exploration. Yes, so this is the summary of the different kinds of results. I will not dwell into it. This I have shown in my previous lecture. And from Chandrayaan 2 to Chandrayaan 3, this also I have spoken about how Chandrayaan 2 observations have led to Chandrayaan 3. And there is a lecture by Ms. Meghala on Chandrayaan 3. So let us listen to her lecture. And there have been a lot of social outreach and capacity building program by ISRO on the lunar science and exploration. And we have organized science meets with experts. We have done data analysis workshops. We have also reached out to the students in different schools as well as colleges to tell about the story of the moon. And also, I mentioned on the previous day, this book is also present for all of you. You can just go to backup slides. No need to show. I'm done.